Welcome everyone to lesson 2.12 from Precalculus, which is all about logarithmic function manipulation. We're going to be talking about identities and properties of logarithms, so let's dive in. Logarithms and exponentials share a lot of identities, share a lot of properties, and we're going to use those properties to manipulate logarithms in ways that we really can't with some other functions. So the first property we're going to talk about is the product property. So this means that if you add two logarithms together that have the same base, it is equivalent to having a logarithm, a single logarithm, where the inside, the argument of the logarithm, is evaluated by the arguments of the two logs you're adding multiplied together. So addition on the outside turns into multiplication on the inside. Why does this work? Well, if we think back to exponentials, remember that a logarithm is equal to essentially an exponent. If we have our manipulation here, log base b of a is equal to c, means that we have b to the power of c is equal to a, meaning that a logarithm is essentially equal to the exponent in the original equation. When it was rewritten to be a logarithm, the exponent moved down to be regular playing field. So if we look at exponentials, if I multiply results, if I multiply b to the power of x and b to the power of y, if I multiply two results, that is the same as adding the exponents with the same base. So if I multiply results are on the inside now, it's the same as adding the exponents. Interesting connection there. And the same thing can be said about the quotient property, where division of results results in subtraction of powers, division of results results in subtraction of powers. Or, again, I like to think of outside and inside. Addition on the outside turns into multiplication on the inside. Subtraction on the outside turns into division on the inside. The last one is the power property, which is a little bit weird, and we're going to explore why it's a little bit weird in class. But for now, you can essentially remember that if you had an exponential raised to a power, that you could just multiply the two exponents together. So if we have an exponential inside of a logarithm, it's the same thing as multiplying the logarithm itself by the power of the exponential. Because the logarithm is a power, or is equal to an exponent, you have an exponent times an exponent. So we have those interesting properties that we can use, and I think that's really cool because there's no other function right now that we really know of, that we've played around with anyway, that has so many unique properties to it. We'll get to trig, which has a lot of unique properties, and that's also really cool. But logarithms have such uniqueness to them and the way that you can modify and manipulate them. So speaking of manipulation, we're going to use these properties in both ways. Both expansion, taking something that is condensed and making it larger, and condensing, making something that is large, a large string of things, into a singular logarithm. Which, again, you really can't do with polynomials. You can't do so much with exponentials, but you can with logarithms, and I think that's really cool. So if we start with the first one here, we have log of 4x squared y. So the first thing I see is I see a lot of multiplication. So every time we multiply something, we're going to break that into its different logarithms being added together. So this is equal to log of 4 plus log of x squared plus log of y. And there's one last thing that we can do, and that is we can take this x squared and we can bring the power down. So log 4 plus 2 log x is equal to, not equal to, is plus log y. Do you need the parentheses? You don't need the parentheses if you have a singular term. I just really have gotten into the fact that logarithms have some unique properties when you don't know exactly what's going on. So I include more syntax than is necessary sometimes, solely so I don't get confused on my end. Here we have division. So first thing we can do is we can rewrite division as subtraction. So we have log of the cube root of x plus 5, subtract log of y squared. The cube root is the same thing as the 1/3 power, so we can rewrite this as log 1/3 of the log of x plus 5. That's ugly. Plus 5 minus, and then we can bring the power down for the y too, so 2 log y. And we could stop there, and that is fine. And normally I would stop here too. You may see in some practice, and you may see on some assessments, this 1/3 being turned into log of x plus 5 divided by 3. Just remember that a fraction here, we can bring the denominator down. We can use the rules that we've previously used in math to simplify things, and you may see things in these forms just because they're equivalent. So don't be too upset at that, but we did turn one logarithm into many, with the logarithms themselves having no exponentials inside them. So that is the goal of expansion, is you're trying to break it apart as much as you can and have no exponentials left in your inside your argument, inside your logarithm. So condensing is the exact opposite. I want to write everything in terms of one logarithm that is nice, neat, and pretty. So the first thing I can do here is I see coefficients. Coefficients become powers. So this becomes 2. No, it does not become 2. It becomes the natural log of x squared plus the natural log of the square root of y plus 1. Then the plus turns into multiplication, so this would turn into the natural log of x squared square root y plus 1. And that would be it. There's nothing more we can really do there. And if you notice, we can't combine the logarithms when they have coefficients. We have to bring the powers up first. And something else weird is if you have addition inside your logarithm, we have no property for that. We have no identity for that. So addition inside of a logarithm doesn't break apart, doesn't condense, doesn't expand in any way. Now we've got some interesting things here. We got 3 logarithms. So let's take our time here. First of all, we can bring the coefficients as powers. So the natural log of ab squared squared minus the natural log of c cubed plus the natural log of the cube root of d. Now, this one's a little bit weird. A times b squared is a squared b to the 4th. So I'm going to skip that step when I go forward. But so making this all one logarithm, in the numerator, we're going to have a squared b to the 4th. Subtraction means that the c cubed is going to go into the denominator. Addition means it's going to become in the numerator. So we're going to have that cube root of d. And that is it for condensing and expanding. If you have any questions, make sure you write them down so you can ask them in class. So that's all fine and dandy. Logarithms are great. Mr. Whaley likes logarithms because they're weird. But I don't like logarithms because my calculator can't help me. If you have a scientific calculator or your phone, for example, you will usually have an ln, a natural log button, and a log button, log base 10, where it's just a common log. But if I have log base 2 of 4, well, I know that 2 squared is 4, so log base 2 of 4 should be 2. How do I get that answer with a calculator? And this is where mathematicians had devised and found a change of base property, where we can take any logarithm and we can write it as a new base. And what that is log base b of x can become log base a of x divided by log base a of b. So we're taking a logarithm and making it into a quotient of 2 logarithms of the same base. Why is that important? Why a? Well, a stands for any log base. So we can choose the common log, base 10, or we can choose the natural log, base e. You could choose log base 2, the binary log, if you wanted to. You don't have to. I wouldn't. But that can help you out, and you can find and evaluate logarithms with any calculator you have. But in a TI-84 specifically, and some other calculators that are fancy like TI-84s, you can find the evaluation of a log without changing the base at all. So in the TI-84 calculator, it's found by going to the math button and searching for log base option. We can talk about that in class, make sure you ask. So let's now combine all of these properties with what we learned last time. Last time we learned about the functions themselves, transformations of those functions, and I alluded to and showed you an example of where 2 transformations have the same two transformations produce the same graph, where they're different transformations. One was a translation, one was a dilation, and they produce the same curve. So let's see what happens here with this one. So we have log base 2 of 4x. We know that multiplication on the inside turns into addition on the outside, so this is equal to log base 2 of 4 plus log base 2 of x. Log base 2 of 4 is 2. So this is equivalent to log base 2 of x plus 2. So what does this mean? This means that a dilation by a factor of, in this case, it would be b squared, dilation by 1 over b squared. It's a horizontal. Dilation by b squared is equivalent to a vertical translation of, in this case, it would be 2. Now, I was a little bit generic here because I wanted to make sure that it would work for all. The reason why it's a 2 here isn't because the base was a 2, it's because 4 is 2 squared. So we got to remember that that's why the 1 over b squared turns into 2. So it's not going to be, you just have to be careful. So again, we have these weird, this weirdness. I don't like this notation. And again, the reason I don't like the notation is because of how ambiguous it is. Hopefully at this point we've talked about and you've explored the reasons why it's not good to have ambiguous notation. So again, we are saying that this is the natural log of x minus 4 squared. So let's do what we can, knowing what we know. And using transformations, and actually no, using modifications, using the identities and the properties we've established, this is equivalent to 2 ln natural log of x minus 4, right? So we would say that this is a vertical dilation by 2, and then it is a translation. In this case, it would be right 4. But if you haven't already noticed what's weird about this, I want you to graph this in Desmos, and I want you to graph this in Desmos, or a calculator if you have a graphing calculator available to you, and look at what's weird about it. I don't want to spoil anything, but I would definitely write down something weird about it and make sure we bring that up to talk about it. And that's going to allude into this idea of the power property isn't always as it seems, and we have to have a discussion about it. So make sure you ask, and we will have a proper discussion about it in class. Otherwise, if you have any other questions, please make sure you ask, and I'll see you in the next video.